So today I'm gonna be going through Green's theorem, one of the useful tools in solving line integrals in calculus, right? So with that said, I'm just gonna be quickly going through the definition of the divergence of a vector field onto it. So let F bar be a vector field on R2 if the first order partial derivative of the component of x exists at x uh, in R2, then the divergence of f at x is given by this. So this is simply taking the, the partial derivative of the components of f. You take the first component of f, which is f1 with respect to x, and then f2 with respect to y. But then for like any general interval, which is when you are in Rn, this is how you find the divergence of, f, right? So let's just go into the definition of the divergence form of Green's theorem. So Green's theorem has two forms. It is the divergence form and the standard form. So here I'm gonna first go through the divergence form, and then I'm gonna go through the standard form. So the divergence form, let D be in R2 be an open bounded set with boundary, a piecewise smooth, simple and closed directed curve C, and let F be a vector field on R2 if the components of F have continuous partial derivative on an open set containing D union C, then F, the integral of F is given by this, right? So that's the formula for the divergence form. So a simple curve, it's a curve that does not intersect itself. So meaning the initial point equals to the terminal point. For like example, if we have something like this, see that? So something like that, it's a closed and simple curve. It does not intersect itself. And then if we were to have something like this, then this is closed, but it's not simple because it does intersect itself here via the origin. So this is not a simple curve, but the one that I drew initially is an example of a simple curve. It does not intersect itself. Then a closed curve is the curve that its initial point equals to its terminal point, right? So that's the formula for the divergence form. So in the exam or semester test, they wouldn't necessarily tell you which form of Green's theorem to use. So you'll have to know which one of the ways is like noting that this formula differs. The left hand side of the formula differs from the one of the standard form of Green's theorem, right? So I'm just going to demonstrate divergence form using this example below here. So here they say use Green's theorem, the divergence form, to evaluate the integral of this. So you see, if they say evaluate integral this, so you know that this now tells us that we're gonna use divergence form because the left side of the formula matches with this one. So we're gonna be using the divergence form where f is given by this and c is the boundary of the region enclosed by the parabola y equals to x squared and the line y equals to x. So when solving this, the most important part, which is where most students are likely to like get it wrong, it's about determining the integration limits, right? So if you get that right, everything should just follow easily. So Determining the integration limits, you're gonna have to draw your region. So if they say C is the region enclosed by these two graphs, so you have to draw these graphs in order to see where does X move from to and where does Y move from and to. So with that said, so I have already drawn my graphs here, so you can see that upper graph is a graph of Y equals to X squared, and this is Y equals to X. So they enclose this region, so this makes my region C, right? And if you were to find the values of the intersection here, you will find that X equals to 1. While finding this value, just say X squared equals to X, right? And then you will find that they intersect at X equals to 1 and X equals to 0. So since we're looking for the 1 here, so this means that X equals to 1 here. So with that said, you can see that in this region, X moves from 0 to 1, and um, remember Y equals to X and Y equals to X squared. So in this region, Y equals to X squared is the below graph and Y equals to X is the above graph. So meaning that Y is less or equals to X and Y is greater or equals to X squared. So meaning Y moves from X squared to X like here, and X moves from 0 to 1. So with that said, we have our everything done, which is getting the integration limits correctly. So with that said, so you just write down the formula there. So here we're gonna integrate with respect to Y first. Remember X, we have values of X, and then Y, the integration limits are in terms of functions. So we first integrate with respect to Y, right? So Y moves from X squared to X moves from 0 to 1. So here you just take the divergence of this, which is you take the derivative, the partial derivative of the first component, which is y plus ln x, with respect to x. So you're treating y as a constant, so you're just integrating ln x, which becomes 1 over x. And then the second component, f2, is 2x plus x e to the y, and you're taking the partial derivative with respect to y, meaning y is the function, right? So x is just a constant, so in this case this falls away and e to the y does not change, so e is dragged along into this. So we've taken the divergence of f. So now we integrate with respect to y, focusing on the inside integral now, right? So we integrate this with respect to y, we get this, and we're taking the integral from x squared to x, right? So you substitute this back in, you get this. So now you're integrating this answer that you got here with respect to x from 0 to 1. Well, you're gonna get 2 minus e over 2. Well, most of you should be comfortable with integrating some a function of such nature. Well, in this case, you're gonna use integration by parts for this case, in that case, right? So this is our answer, 2 minus e to the 2. Now we'll jump into the standard form of Green's theorem. So the definition says, let D in R2 be an open bounded set with boundary a piecewise smooth, simple closed directed curve C that is positively orientated. So with the standard form, we have to consider the orientation of a curve, whether it's negatively orientated or positively orientated, right? So if it's positively orientated, here we have a plus, like in this case. If it was negatively orientated, you make this a minus, so it's negatively orientated. So with respect to D, and let f be a vector on R2 if the components of f have continuous derivative. So it's always important that the components of f have continuous derivative. On open set D union C, then this is the formula for the standard form. So here you take the partial derivative of the second component with respect to x, you subtract the derivative of the first component with respect to y. So let's get into the example that I'm going to be demonstrating this one. So you can see that the left side differs for the standard form, right? So use the Green's theorem. So we're using the standard form to evaluate this integral. So you see, if they say evaluate such integral, so you know that you're using the standard form. When f is given by this and C is a boundary of the region bounded by this and that, right? So important thing to note, so C is bounded by these two graphs. So now we're gonna have to first draw these graphs in order to identify our integral limits, right? So this is x equals to y squared. This parabola, remember you just now treating x as if it's a y-axis, so you just shift the parabola and then it faces the positive side of x, and then x equals to 4 is just a vertical line. So this forms this region, and this becomes our region C, right? So to find where these two graphs intersect, so you just say x equals to 4, right, should be equal to x equals to y, meaning y squared equals to 4. And then you solve for y, you get that y equals to 2 equals to plus or minus 2. So y moves from, in this region C, y is from minus 2 to 2, and x is bounded by these two functions, like you see it. And remember, x is bigger to the right and smaller to the left, right? So, and x equals to 4 is to the right of the x-axis, and x equals to y squared is to the left of region C. So x moves from y squared to x equals to 4, which is, we have these as the integration limits for region C. So x is from y squared to 4 and y is from minus 2 to 2. So with that said, we get into the answer. So the right side, you take the partial derivative of the second component with respect to x. So the second component is x minus y. The first component is e to the y plus x. So you take the partial derivative, which it becomes 1 in this case, and the partial derivative of the first component with respect to y, it becomes e to the y, because x is now a constant, and then this doesn't change when we differentiate it. And then now we first take the integral with respect to x, right? Because x, we have a function, see it, and but then y moves from values to values, and we would like to get a final answer as a value, not a function. So hence we first integrate with respect to x and then integrate with respect to y. So now we're integrating this with respect to x, which is not so hard. So let's just multiplying this by x, which is that, and then we're taking it from y squared to 4. So you substitute these values here, and then you get 4 when you put in this, you get 4e to the y, which is then you put in y squared, you get y squared, you put in y squared where there is x, so you get y squared e to the x, right? So now this is a case of integrating this. So again, for this part, you just use integration by parts, right? IBP. So you use integration by parts for that part, and then you should get this as your answer, and you take in your integral from -2 to 2. So that's it. So now those are examples that I was using to demonstrate the standard form of Green's theorem versus the divergence form, right?